So that's the magnetization. If you like to think about it as kind of like dipole moment per unit volume, that's exactly what this is. If I wanted to take the total strength of this, I could get the magnetic moment, and this is the magnetization. Now, the thing that makes magnetics, which is, I mean, it's like physically, it's just so simple, right? I've got magnetic particles in here. I put on a magnetic field, they all kind of align, and I end up getting, you know, the quantum conditional. So that is really a simple kind of concept. What makes it interesting is that this field that we're going to be talking about here is really the Earth's field. So the Earth, like this, and we can think about the Earth as being generating a magnetic field that's kind of here at some point A. I have a magnetic field that's coming in a particular direction. So at point A, the magnetic field is coming in like this. Magnetization is going to, you know, be in that particular direction, and then the magnetic field lines from this, you know, are going to be that of a magnet. Okay, so that's the idea. Anything is going to get magnetized, but it's going to be in a direction that depends on where you are with respect to the North Pole or the equator. So if I'm sitting here, for instance, at the equator, then the magnetization, this thing is going to get magnetized in a horizontal direction. If I'm sitting over here, it's going to get magnetized vertically. Okay, so those are the basic elements. And then what we want to do is we're going to kind of walk through this whole procedure today in a little bit more fine-grained detail. But the thing that is going to be primarily occupying us is what do we actually measure? Because we're actually going to measure the sum of whatever magnetization is here. So let's suppose we've got some kind of a magnet here. That's going to give rise to its own magnetic field. And we're going to measure the sum of the Earth's field and this guy. And then we're going to try to work with that. When you go out into the field this afternoon, you're going to have what's called a proton precession magnetometer. Field that's obtained from the object. So we're going to walk through this thing here. This is going to be what you're going to measure. And then as far as you're concerned, you're just really interested in something about this little guy who's buried here. So you're going to generate an anomaly, which is going to be delta V, which is going to be onto the direction of your field. So that's where we're going to go. And I'm going to introduce an app that will kind of take you through that. So let me It's highest at the poles, lowest at the equator. And then it also had a declination, which was the angle that it would point compared to magnetic north, as well as the inclination, which is the angle that the magnetic field is from the horizontal position. And so in Vancouver, where we are here, the inclination is about 70 degrees. So it's actually, for all intents and purposes, it's pretty much vertical. So that's a good way to kind of think about it. And yeah, the declination was about 16 degrees. So we're not 100% true north, but actually not too bad. I had meant to show you this. It's an illustration of an app that you can download. We'll probably come back to that, but actually by the time you get through today and what you already had in the lab, you'll realize that your iPhones have got a magnetic sensor on it, and here's the axis. That's the important thing. So if you're holding the iPhone out in this direction, the z-axis is probably up this way, and the x and the y are like that. And then the app will give you a running value of what the magnetic field is, the x, the y, and the z components as a function of time. And you can just sort of see how things vary. Okay, so just a second, let me get my coffee cup. Anyway, so we'll probably come back to that. You'll see that in the at the beach Saturday. So here's our magnetic survey. So the first part was that we've got an Earth's field V sub 0. Okay, that's our source. And now Earth's field are going to magnetize anything. And we're going to put that as a symbol V sub A. So here's what I just talked about. So we have material that's susceptible, then the magnetization is going to be given by this. And that magnetization is the dipole moment per unit volume. Or you could break that out, it has units of amps per meter. The total magnetization or magnetic moment that you get is the integral over the volume of whatever the magnetization was. So that's the same equation I just written down here. And that is going to have units of amp meter squared. And this is a vector. So at the end of the day, whatever object you got there is actually going to kind of look like a magnet. So that magnetic moment is going to be pointing along the axis. So it's got a particular direction, it's got an inclination, and it's got a declination, but it's a vector. So here's what it looks like. So if you actually were able to draw the magnetic fields lines from here, so here's your magnet, and then the field lines emanate from the North Pole, go into the South Pole. This is actually a mathematical description. This is how you would projection. So if I've got two vectors, one that looks like this, and another one that looks like this, then there's only a certain projection. I mean, you can think about a light coming down. That's the best way to do it. Think about this. Think about another vector coming up here. amplitude of A times the amplitude of B times cos theta, where cos theta, that's the angle between these guys. This concept of projection is the key to all of this, because we're going to be really working with a vector, but then we're going to measure something. And that measurement is either going to be the projection in the x direction, projection in the y, or the projection in the z. That's the three components. So I've got a vector, I need three components, so I do that by finding what the projections are. So this formula in here basically says that the magnetic field kind of depends upon r is the distance that you are away here, so it's a radial vector, and this tells you what these field lines are, what the value and the direction is at this point. We're not going to go into this in too much detail. The important thing about this, however, is that B varies as 1 over r cubed. There's an r here, so that's r squared, and r fifth. So this term is 1 over r cubed, that's 1 over r cubed. That's a fundamental thing about dipoles, is that the fields fall off as 1 over r cubed. So they get smaller. You double the distance, you reduce the amplitude by a factor of 8. Okay, so now let's look to see what we've got, because we're going to measure the sum of the Earth's field and its anomalous field. So here's what we have. We've got the Earth's field coming in like this. It's going to magnetize something. So the object under here is going to have magnetic field lines that look like this. And then we're going to measure the sum of both of these things. So let's take a look. Let's suppose we're over here at B. And say, okay, what are we up against here? So first of all, B naught is coming in like this. So that's this red line. But if we look at the anomalous field, we're sitting right here, the magnetic field lines are coming up like that. And so I'd have a vector, my anomalous field vector is kind of, it's an arrow that's pointing up this way. Okay. So that's like this. And then I'm going to add the two together, and that's going to be the final value that I have to make. Okay? So I've got this is a vector, this is a vector, and here's my sum. If I move over, so let's suppose I'm over here, now it's a bit of a different story, because B naught, the Earth's field, is in the same direction. But now BA, watch what this does. So my anomalous field is coming up like this, and it's going down. So my anomalous field is coming in like this. So now here's B naught, here's BA, and here's the field. Okay? So that's it. You're just simply adding, you're always adding two vectors at a point, and you're going to get a final field. And then now we have to measure something. And what I want to do is to take you through, well, I could measure the components, an x, a y, and a z component. Or I could measure a total field value. Those are my options. Let's work with the total field data, because this is what you'll see when you see maps. Generally, this is the thing that always is going to be visible to you. And we're going to measure B as being like that, but a total field magnetometer just measures the amplitude. So it's like this. So I really have, so here's what we had. B naught is equal, B is equal to B naught plus BA. That's what I have. What I measure is just the amplitude. And then that means I put the amplitudes up here, and then I'm going to subtract the Earth's field from it. And so long as this actually holds, so long as the anomalous field is much less than the Earth's field, then effectively this total field anomaly is the projection, that word, of the anomalous field onto the direction of the Earth's field. Okay, so that is the key. Yes?
Can you ever get EA being larger than B0?
No.
Okay.
No. So you're where you get really kind of screwed up, however, is when you go up into the north, into the North Pole, okay, and or towards there, and then this relationship is no longer true. And actually, neither was the answer that I just gave you. Okay. I spoke too quickly. Okay, so your question was, can you ever get a total field that's actually less than B naught? And so if you're sitting up here, and suppose you've got some B naught that's coming in like this, okay, and now we've got an anomalous field, suppose that's sitting up over here, okay, then if this anomalous field is opposing this, then this value here will be the combination, because it's vectors. B is equal to B naught plus BA. So this will actually be, the magnitude of this will actually be less than the magnitude of this, and so you will get a negative value. Yeah, so that's actually exhibited right here. So if I look at that difference, I actually get a negative. So here's the point here. So think about a situation where you've got something buried, it's magnetized, and then just think about the magnet, okay, because now you can visualize how the fields are going to go from the magnet. And then you're looking at an anomaly that is the projection of those fields onto whatever direction the Earth's field was. That's your anomaly. So here's how you kind of think about that. So imagine that B naught is like this, and then BA was just this little guy here. I mean, in reality, B naught is like 50,000 nanoteslas, and an anomalous field of 1,000 nanoteslas is actually pretty big. So even at this scale here, it's not really quite the scale. But if we measure the sum of those two guys, then here is B. And now I think about taking this B and I sort of bring it back here. So I'll keep the same amplitude, bring it back here. And you'll notice that where it intersects this axis here is almost the same as the projection of BA onto here, which is BA goes through. So there's the rationale for why when I take the difference between these two amplitudes, because one is really big and the other is kind of small, then that difference is just kind of related to that projection. Oh, why is this so small? Okay, so what I want to spend part of the rest of the day is looking at one of the apps. So if you sign on to the GPG, there's actually a couple, let me close this. So first of all, there's magnetics up here, and there's also something down here called apps. If you click on this guy, it's going to open up like a sort of an index to a whole suite of applications, which we will do. We're actually going to look at a particular app that's in the magnetics, and so let's just do that. So here's the magnetics. Here's our magnetic dipole applet. And when you get here, there's actually quite a few things on this page. So there's going to be, first of all, some kind of general instruction about what, there's a picture of what the app is going to look like. By the way, how many people actually tried to open this up? Oh yeah, and successful? No? Okay. So if we just kind of scroll through here, so here's a bit of a background summary, and then there's some stuff in here called learning with the dipole app, and there's a whole bunch of questions there. So we're going to use those. There's also something here called binder, and this is how you're going to access the app. So I'm going to press on this guy, and then these wheels here are going to come up and they're going to spin around for a bit. Generally not very long, but depending upon what the usage is, it could take a little bit longer than the other. So what this is doing is this is spinning up an incident of Jupiter. So Jupiter is a way of kind of interfacing between a user and what he wants to do and use for software, and some web deployment of this. So we've got there's some server someplace that has now been spun up and is going to be running this app. Okay? The thing about this this app, as soon as it comes up, you'll see there's a whole bunch of cells. So these guys here, there's a cell, there's another cell here. We can activate each one of them, or we could take a simpler route, and if you do go under cell up here and you just run all, then that basically gets the software that was used to generate this app, gets that activated, and now you have a live interactive app at your disposal. So let's just take a look through there and see, kind of see what we've got. When it opens it up, you've got a set of slide bars here. Well, first of all, you've got something up at the top that says dipole or monopoles. So a dipole is what we're talking about now. When you do the lab, we go to analyze the stuff in the lab, you find that, oh, wait a minute, we can even do something simple. We talk about a monopole. It's a dipole, and it's going to be orientated so that it's got a particular inclination and declination. So the inclination slider button goes from like -90 to 90. So if we're sitting down here at this end at -90, that puts us at the South Pole. If we're at 0, that's going to be our datum at the equator. And if we're sitting up here towards the North Pole, or actually we're at sort of like 70, then that's effectively what we're going to do. Okay? Then declination is telling us which what the orientation of that dipole is with respect to north, and there's 0, and it could be something that looks like this. I could make it even more dramatic by changing the inclination. So you get things that look like this, like this, like this. So depending upon, for instance, where you buried the object or where you're doing the survey on the Earth, I mean, you could get a picture that looks like this. This is actually the total field anomaly. Or you could get something that looks like that, whatever. Okay, so this is actually the same, same strength dipole, just sort of buried at different orientations for the field. Of the survey in meters, and in this case here, it's going from about -35 to 35 meters. So that's X and Y are the same. And there is an option here for data spacing. Talk about that in a second. And then there's M, that's the magnetic moment of the dipole. So if right now it's set to 30, if I change it, if I make it 300, increase the value. So the value up here is 1.27 nanoteslas. If I increase that, oh, here's a question. I had it at 30, and I got 1.27 nanoteslas maximum value. If I now increase the strength of that dipole to 300, what would I expect to have on the data? Anybody? Basically, if you're sitting on the axis, didn't actually dissect that particular formula, but if you're sitting on the axis, you get an expression for the magnetic field that falls, the magnetic field strength is m over r cubed. So we're sitting over here, here's our magnet, and here's our distance r, and then the field falls off as 1 over r cubed, but also depends on that. Okay, so now if I had an m is equal to 30, I got 1.27 nanoteslas. If I have m is equal to 300, what should I get? How much?
12.7.
12.7, right? So this says that the magnetic field should vary linearly with the strength of the magnet. So I can try that. And that's, I'm sure you can see it, but it is about 12.7. Okay, so that's something. Then there's also a depth of burial. Okay, so the depth of burial is the distance between the center of the magnet and your instrument. So when you go down to the beach, you're actually going to have a sensor almost 2 meters above the ground. So the sensor's above. And then you're going to have an object here that is below. So right now this is at 10, right? So that's synthetic is at 10 meters. So if I decrease this, let's suppose I decrease it by a factor of 2. Okay? So what does that make it? Come on. All right, thank you. Okay, so if I make it 5, then how much? So right now it's at 12, right? So the data is equal to 12 nanoteslas. So if I make this 5 meters, what's that going to do to the amplitude? How much? Oh, I can hardly hear you. How much?
I'm confused.
Okay, so it was at 12, okay? So when it was 10 meters down, the value was 12.
Yeah.
Now I'm going to raise it up to 5 meters.
Yeah.
Okay, so now what's the signal? So it's going to be what?
Oh, I don't know.
No, I think you were right. I just couldn't hear.
Factor of 8.
Okay, good. So factor of 8. And 8 times 12?
96.
Thank you. Okay, so let's see. So if I reduce the depth to 5, what happened? Soggy.
Well, you're looking at the maximum. Can you go back? Try like as the north pole, like your information is 20, so you try 9 maybe.
A second.
Okay, so let's bury it at 10 meters. Okay, so we're burying it at 10 meters. Let's just change the length a little bit. Okay, so now we're at the North Pole. We're at 10 meters depth, and now we've got 42. Okay, so our data is equal to 42. Okay, and now we're going to change it to, so this is at depth is equal to 10 meters. So if we make it at 5 meters, we've got a factor of 8, which is what, 336 or something? Oh. Okay, so let's see if that works better. Ha.
Can you increase the, like, decrease the data spacing?
Okay, we have found an interesting bug. There's something wrong. Okay, so this is kind of cool, right? So we put these together. You've got a mathematical formula, right? So we trust the formula, right? And so the computations are supposed to prove that. We basically had that B varies as m over r cubed, right? So we increased this and we linearly increased the data, so good to go. We decreased r, factor of 2, we were expecting 8, didn't happen.
But so, yes, the reason why is that is like the receiver is at above 1 meter. So it's not exactly like so you're changing from 10 to 5.
Oh, is this the depth below the
yes,
Earth?
So
oh, okay, so we.
Surface.
A detail, which I forgot. Okay, so these data in the lab or in the app are 1 meter above. The depth, okay, is below here. So if I put depth is equal to 10, then we're really 11 meters down. So let's do the following. See if we get this right. So let's bury it at 9. So now we're back to a total depth of 10 meters. Okay. Oh, but we're not going to be able to do halves, right? Oh, can we do halves? So if we're 10 meters below, then we have 59.6 nanotesla. So now I'm going to change it to be 5 meters below.
So 4.
So now I'm going to make it 4. Okay, so now we're 59 points, that's like 60, and times 8 is 480. So we're actually hoping for that number, right? Ready? Wow. So that's 480, 478. My case risk. Okay. So that's this is the kind of thing that you can do. Let me also talk about the different projections. Yeah.
Where does it say it's 1 meter above the ground, or is that just assumed?
No, it says in the notes that it's 1 meter above the ground. I'd forgotten about that.
We're thinking about putting a receiver, like you're holding a receiver.
Okay. Yeah.
Okay. So let's talk about the profile. What you're seeing here are the data. So let me put it back a little bit more towards, be a little bit deeper. So here we have 44 meters on the side. It's buried at 13 meters depth, and you kind of get a sense about how the relationship between this depth of burial, okay, and sort of the size of the image that you're seeing. So here it's like 13 meters depth, and you're kind of covering 30 meters on the side. If you're to look at what these fields are, so this is the total field anomaly. So it's the projection of the anomalous field onto the direction of the Earth's field. So let's just walk through that. So here's the Earth's field, or here's the Earth, and here's the Earth's magnetic field coming in like this. And now I've got something in here that's magnetized in this direction. Okay? If I sketch you think about these as being the dipole field lines. So this is the anomalous field, okay? Now, the number that I'm going to get out from doing this total field anomaly is the projection of this guy, whatever I have here on the anomalous field, onto this direction. So if I'm sitting here, if I'm sitting right above here, then the anomalous field is coming vertically down, so it's parallel to the Earth's field, and so I'm going to get the total magnetic field from this thing as a number that I'm going to have. So sitting, maybe let me do it here. So now up here on this plot, I'm actually going to plot my anomaly. And so at this point here, it's actually going to be positive and it's very big, right? Now what happens if I go up over here? So here, if I'm on this side here, so now the magnetic field lines are coming up like this. So here they're coming up like this, and someplace over here. So my anomalous field is actually going to be pointing in the opposite direction. So at some point over here, I'm expecting to get something that's really it's a bit negative, and then my anomaly is going to come up like this. So in this particular scenario, I'm going to get some negative values here, but I'm farther and farther away from the magnet. Remember that 1 over r cubed means that these guys here are not actually going to be very big. But what I'm expecting is basically some kind of anomaly that looks like that. Now, if you look at this body here, you see that the maximum values is a positive value, 21. And the negative values are small. There's some negative values here. That's the dark blue. So that's all kind of consistent with this. If I plot a profile across here, so I can plot either an east-west profile or a north-south profile, then this is what I get. So I'm going to get a line that kind of looks like this. And one of the interesting characteristics of this is that I can compute the half width. So if I compute the half width of this, if I compute the half width of this line here, I find that it is about 13 meters. So this is about 13 meters. How does that compare to actually the depth of burial? So if I look at the depth of burial, it's about equal to that, right? So I've got a depth of 13 plus 1 is 14, so that the half width of this guy here is approximately equal to the depth. So we can test that. So that's what we might learn from this as one observation. Does it mean that it's going to, if I change if I bury it shallower or deeper, I'm going to get still the same relationship, or how does that work? So let's just try it. So that instead of burying it at 13, let's bury it at, let's say 5. So if I bury it at 5 meters, now my half width is 5.9, right? So and if I bury it at 5, I'm 6 meters. I'm 6 meters below the sensor. So again, this thing comes up to be equal to the depth. So that's actually kind of nice, and that's actually a very powerful thing, right? Because you get some type of anomaly. Right? It's something that looks like that, and you could look at the anomaly, and just by doing some simple analysis on this, kind of get like, okay, I think this thing is, it's buried 10 meters or 5 meters. I mean, that's really important. Suppose you're looking for just a buried drum or something like that, right? Then, it's going to act like a dipole, and if that half width of the curve comes out to be, 4 meters, then it's like, okay, that's about how far we're going today. So that's something that you can experiment with. The other thing is date. Yes.
Does that approximation only work when you're in 90?
Yes, it works best when it's 90. Let's try it at let's try it at 0. Okay, so this now. So let's go to 0. So now we're at the equator, and let's make the declination. Make the declination 0. So here's actually now what that plot looks like in that direction. I could also go north-south, profile north. Okay, so now suppose I'm going this way. Okay, so I got something then that looks like this. The depth is 26 meters, okay? And the half width is 20.7. So it doesn't exactly hold. It's true. It was that formula. This was derived, for a vertical magnetic field and to see. But even if we did something that looked like this, so you use the same half width rule, like, okay, well, I'm going to be approximate. But then if I change the depth to 13, or let's suppose 9, then I've got, a half width of 7. So there's, it's kind of doing the same thing, but you can't, work with it as being exact. Yeah. Somebody have a question? The other thing that I want to stress here and have you play around with is data spacing. So what this number here tells you how frequently you're taking data. So this is sampling every 0.2 meters, but it's always going to cost you money to take data. So you might want to sample less. And so you can experiment with that by simply saying, okay, if I'm going to sample every, well, that's a bit extreme. So if I sample every 2 meters, so remember this was about 40 meters across here. So every 2 meters, it's still 20 points. And 20 times 20 is 400 data, it's a lot. So now your anomaly is starting to look a little bit different, right? You're coarsening it up. You can see like I still got the same shape in here. So I think maybe I've kind of captured things. But if I now make it even coarser, so if I brought up something that looks like that, now you can see you're starting to have a poor map anomaly. but maybe you still have something. But if you make it really coarse, decide, oh, I only want to do 10 meters or something, it's gone. Right? So this is kind of a fun thing to play with, right? Because it really helps in that survey design. You can kind of decide, okay, how often do I need to take data to do this? So let me just close up here by doing one thing. So if you go back onto the GPG, onto the magnetic outlet, and then you can launch it with binder, okay? That's this button up here. And then here's the thing that's of interest. So below that, we've got a little bit of a summary, and this is what you're going to see for each app. There's going to be a little bit of a summary, kind of giving you the highlights. And then there's stuff called learning with the app. Okay, so we spent a fair bit of time thinking about this, trying to think about, okay, what kind of questions can we ask you to get you engaged with this? Because I think this actually might be one of the best ways of learning. We just give you an app and give you some slider bars, and it's like, okay, saw some different pictures. But if the moment that I ask you a question, and you actually have to think about, hey, which slider bar do I want to use, and what am I expecting to get out, then you're interacting, and then you can learn. And with all of these things, the way to use an app is actually to do exactly that. You have a question, and then try to sketch out for yourself what you're expecting to see, okay? Try to force yourself, sketch out on paper, whatever it is, try to answer what it is you're asking, and then you press the button. Okay? When you do that, that's when the learning happens, because either two things happen. Either the picture that you get out matches what you'd already sketched out, in which you say, good job, me. Or the other is like, it doesn't match, which means, okay, I've got something to learn. So that's the procedure. I believe actually that these apps have got a tremendous power from the point of view of just learning the concepts and the applications. So I'm hoping that you will kind of go back, take a look at these things, and especially in this case here, the big one of the big things is just burying things at different locations on the Earth, and then just trying to get an idea of what the anomaly is actually going to look like. If you can sketch that out, then you're going to be good to go. There was a question up there?
Yeah, does the lab start at 3 sharp today?
The lab is,
Does it start at 3?
it does.
So what's if we have class beforehand?
Pardon me?
If we have class beforehand?
Oh, well, you got 10 minutes to get down to recreation. You're fast. You're not old like I am. But you can dance. No, they'll still be there, not to worry. And clothing is optional, actually. I am going to bring a camera.